Hey everyone, welcome back to Math 261. This is Scott. Let's get started. What we're going to be doing now, like so many other sections in this first chapter, is we're going to be taking a first bite at an apple that we will come back to many times throughout the course of the course. So this is just your very first dose of what are called linear transformations. So this is section 1.8, intro or introduction to linear transformations. Alright, so this is a very first basic introduction to an idea that plays a big role in basically not just the rest of this class, but the rest of math classes that you take after this. They may not necessarily be called this, but they're lurking behind the shadows of many of the classes that come in the wake of this one. So essentially here, the idea is that a linear transformation is a function that takes vectors from, for example, Rn to other vectors in Rm. So that's R November to R Mike. Now, specifically, there's a special condition that needs to be applied for the function to be linear. Specifically, we need the function to have the following properties. So specifically, so let's say we'll call it T. T for transformation. So T of U plus V has to equal, so this is the first one, T of U plus V has to equal T of U plus T of V. So you can almost think of this as it has to be able to distribute over addition. The way we say this in this context is we say that it respects vector addition. And then also, if we do a scalar multiple of a vector, that has to be the same as that same scalar multiple of the output. But anyway, so this is not really crucial for us to know right now, but these have to be true for all U and V. For all U, V in Rn, and all C just in R. So this is just part of the legal doctrine of linear transformations. It's not what we're going to focus on in this particular section. What we're going to focus on in this particular section is a very specific kind of linear transformation, the kind that you get when you multiply by a matrix. So there's a specific category, which is going to be the focus of this section. Specific category of linear transformations. And that's going to be matrix transformations. So these are the transformations that you get by multiplying by a matrix. So here's the notation that we use. So we'll say transformations accomplished by matrix multiplication. All right, so now some specific notation that we will be using, some notation and language. Notation and terminology. So we can write the following. So let's suppose that A is an M by N matrix. And we write T, and then you do a colon, and then you do R, N, and then an arrow. Then you do R, M, and the way you pronounce this is T maps from Rn to Rm. And this space right here is what's called the domain. The domain of T. This space right here is what's called the codomain of T. And we write T of a vector x is equal to ax. And we call the result of this the image of x. Oops. The image of x under T. And then we would call the set of all the things that you can get by multiplying by the matrix A, we call that the range. So the complete set of elements of Rm that are images under T of elements of Rn, so that's R Mike, R November. So the complete set is called the range. The range of T. And these are the main pieces of terminology. Now, to see how this actually plays out, and we have all these alien seeming words and symbols, let's see if this is actually going to be as difficult to do as as it is to say. Good news, it will turn out that the bark here is much worse than the bite. So let's take as an example just a matrix. We'll make it a 2 by 3 matrix. So A, which equals 1, 1, 2, 0, 3, 9. And then we'll say that a vector u is equal to 1, 2, 3. And then we can say this. Start saying questions. Oh, and let's say that t of x is defined to be a times x. Okay. So what this means is t is going to be the name of the transformation that is accomplished when you multiply by the matrix A. All right, now we can ask some questions. So we can say find t of u. So that's this vector u. Apply the transformation that involves multiplying by A and see what you get. So find t of u. So t of u, like t of anything else, is the same as A times u, which is the same as just taking the matrix 1, 1, 2, 0, 3, 9, and multiplying that by the vector 1, 2, 3, which is the u. And here you can do this in either of the two approved formats for this. You can do this as these are the weights that go to each of these the column vectors here, or you can do it in the row vector approach, which is to take this times this plus this times this plus this times this. And that's what I'm going to do. That's going to be my default in most cases, I think, just because it cuts out some of the middleman. So 1 times 1 plus 2 times 1 plus 3 times 2 for the first row, and 1 times 0 plus 2 times 3 plus 3 times 9 for the second row, and that's going to equal, so 1 plus 2 plus 6 equals 9, and 0 plus 6 plus 27 is 33. So t of u is what this has been equaling the whole time. So the image of u under this transformation is equal to the vector 9, 33. So this is a transformation, and it has transformed the vector that was a three-dimensional vector 1, 2, 3 into the two-dimensional vector 9, 33. That's the effect of multiplication by this matrix. So that's one task you can be asked with regards to one of these matrix transformations. An alternative question would be the following. So you could ask if it's possible to find the x in R3 such that t of x is equal to 7, 27. So now the shoe is on the other foot. Rather than being given the vector that we're multiplying by, that is the mystery. So t of x, we're told, equals 7, 27, which means a times this mysterious x is what equals 7, 27, which means that we've got a mystery vector x1 and x2 and x3 such that when we multiply by this times our mystery vector x, we get 7, 27, now we see that we would approach a question like this. This is just a classic matrix equation. We would approach that by just our old time-honored, time-tested, official approach of row reduction. So we would set up an augmented matrix. 1, 1, 2, augmentation bar 7, 0, 3, 9, augmentation bar 27. So this is an augmented coefficient matrix that corresponds to the system that this matrix equation also corresponds to. And now we can proceed with the row reducing. So here we've actually got a pretty good looking first row already. The second row though is burdened by a factor of 3 that we can undo. So we'll just take R2 and we'll make it a 1/3 of its former self. So that'll make it more pivoty. And so that'll give us 0, 1, 3, 9. And here now we can use this this pivot that we've made in the second row to clear out the row above. So row 1 getting replaced by negative row 2 plus old row 1. So that's going to be 1. It's going to be now 0. It's going to be -1, and then this is going to be -2. And then down here we're going to have 0, 0, 1, 3, 9. And so what we're going to have here are 2 basic variables, 1 free variable. So the one, actually our row reduction here is done. So what we can do is we can rewrite it now in the form of the matrix, or sorry, of the equations involving the x's. And that gives us x1 equals x3 minus 2. And x2 plus 3x3. Apologies there, due to a technical malfunction, a couple of seconds of video were just lost, but let me bring you up to speed. So what happened was I was taking the equations out here, out of the row reduced matrix here, and I was writing each of the x1 and x2, the 2 basic variables, in terms of the free variables. Here's where it cut out, and then I solved this for x2, and then we need to actually express the solutions to these equations, the x's, the things that we're trying to find here. And we can do this by x is equal to x1, x2, x3. And here that we replace x1 by what x1 is seen to equal. We replace x2 by what x2 is seen to equal. And as for x3, it equals itself. And that's what you missed when the camera cut out. Okay, now we can in turn rewrite this as the piece that involves the x3 and the piece that does not. So x3 minus 3x3, and then x3 again, plus -2, 9, and 0. And so here what we have would be x3, 1, -3, 1, -2, 9, and 0. So this is what x equals. So x is everything of this particular form. So what that means is that we can actually find an infinite number of solutions to this equation, one for each value that we choose for x3. So a solution would be, for example, if x3 equals 0, x equals -2, 9, 0. So this would be a solution, but any other solution would have this form right here. And so as a follow-up, we could ask, is the solution be found in part B unique? And the answer is absolutely not. There was a free variable. We have an infinite choice of what that x3 could be, and so what we have is actually a family of solutions, one parameter family, one for every value. So and the parameter is the x3. So no. Any element of the set, and here's a way you could write it. So you can make a set, and what you can say is you can say what the one parameter family looks like, and it'd be customary here to use a generic letter like t for a parameter, t, s, things like that. So t times 1, -3, 1 plus -2, 9, 0, where t can be any real number, such that t is in the real numbers. So any element of this set would be a solution. So this is a way you can handle it when you get an infinite family of solutions. You replace the parameter, which we wrote above, with the free variable. You replace that with just a generic parameter name like t or s, and then you would just give the formula for it and then make the stipulation that you have to make about the t. So any element of this set would be a solution to that same equation. And then a follow-up, and this is more or less just like a vocabulary question than anything else. If I asked is a, which equals, and then let's say a equals just that same vector from before, 7, 27, is a in the range of t? Answer is yes. And the reason is because there are values of x such that a would be the image of that x under t, and in fact we just characterized them. Yes. And that's because any element of the set from the previous question would be mapped to A. So that's what it means to be in the range, is that it has to somehow be hit by some element from the set. And sure enough, it is. So that is that. So these problems are all actually very easy, even though the language is maybe a little bit forbidding. What it all comes down to is you just have to figure out, are they giving you the input and it's your job then to multiply, or are they giving you the output and your job then is to solve? So the two sides of this coin are, on the one hand, matrix multiplication, on the other hand, row reducing. But those are the only two things that are actually in play here, and so your main job is, once you sort through all the words and all the crazy language, is to figure out which one it is. Is it a multiplication or is it a row reduction? So that's your very first taste of linear transformations, and that'll do it for now, but we'll pick it up in the next section with some more of Math 261. So till then, bye!